In this lesson, you will learn about second derivative test, concavity, and points of inflection. First up, we study concavity. The test that you will do is you will look at f double prime of x, and if it's greater than 0, then that means f is concave up, which we will abbreviate CU. Take a look at this diagram. We can see that the y values are getting smaller as we go from left to right, which tells us that the first derivative is negative, meaning less than 0, which means the graph is decreasing. But for this shape, the second derivative would be positive, which means the graph is concave up. In this diagram, we can see that f is increasing, so we know the derivative would be positive. And this is also concave up, which means the second derivative would also be positive. So both of these curves, this one and this one, are concave up. It's just this first one is decreasing and concave up. The second one is increasing and concave up. Here, when we do a test and the second derivative is negative, then we say f is concave down, which we abbreviate CD. In this diagram, we see that the first derivative will be negative, so less than 0, because the graph is decreasing. And for this curve, the second derivative will also be negative because it's concave down. Whereas for this curve, we see the first derivative will be positive because the graph is increasing. But here, the second derivative is also negative because the graph is concave down. So this shape means we have a decreasing concave down curve. This shape means we have an increasing and concave down curve. So there are 4 possibilities. If the first derivative is negative and the second derivative is positive, then we have a curve that is decreasing and concave up. If the first derivative is positive and the second derivative is positive, then we have a curve that is increasing and concave up. If the first derivative is negative and the second derivative is negative, then the curve is decreasing and concave down. And if the first derivative is positive and the second derivative is negative, then the curve is increasing and concave down. All of the curves that we graph will be one of these 4 flavors. In this example, given the graph of f of x, sketch the graphs of f prime of x and f double prime of x. So here we have this curve, which is f of x. Now there's a couple places on the graph where we know exactly what the derivative is, and that would be here at x equals a. We have a horizontal tangent line, so f prime of a is going to equal 0. So we can come down on the graph of f prime, and at x equals a, we know f prime has to be 0. The same is true over here at x equals c. The slope of the tangent is also 0, so f prime of c is equal to 0, and we can put that on our graph of f prime. So now what we want to do is take a look at the slopes on f. They become the y values on the graph of f prime. So here, the slope of the tangent is a steep positive number. So that would be up here somewhere. Then as the tangent moves here, it's still positive, but it's getting smaller. As we move here, the slope of the tangent is getting even smaller. And when we get to here, of course, we already said the slope is 0, so the value of f prime is 0. So if we connect these points, after x equals a, we see that the slope is a negative number now. It's not very steep, so it would be a small magnitude negative number. As we move along here, it gets more negative and more negative and more negative until x equals b. So maybe that steepest negative value would be about there. After that, the slope of the tangent is still negative, but it's getting closer and closer to being 0. So it's going up towards 0. So we can try to connect those points. We know f prime of c is 0, and then here the slope is slightly positive. Then it gets more positive. Here it's very steep, so even more positive. So now we connect those. So this could be a graph of f prime of x. Remember, we started by having the two anchor points. We knew f prime of a had to be 0, f prime of c had to be 0. We knew that the slope was a large positive number over here. That's why we have large positive values for f prime. Then the slope is getting smaller and smaller, so f prime is getting smaller and smaller till it hits x equals a, where it's 0. Then the slope goes slightly negative, more and more negative. So that's here, slightly negative, more and more negative, till it gets to x equals b. Then it's still negative, but it's getting less steep, meaning less magnitude negative. Then it goes positive and gets steeper and steeper, so the y values are positive, getting bigger and bigger. Now to draw the graph of f double prime, we know that f double prime is just the derivative of f prime. So that means we can use the slopes from the graph of f prime to give the y values on the graph of f double prime. Now, looking at this curve here, it appears at x equals b that the slope of the tangent is 0. So this means f double prime of b is going to have to equal 0. So we come down on the graph of f double prime and make a y value of 0 at b. Now, if we look to the left of b, the slope here is a steep negative. So that would be a negative value. Then here, the slope is still negative, but it's less steep, which means a smaller magnitude negative. As we get closer and closer to x equals b, the slopes are negative, but getting closer and closer to 0. After x equals b, the slope is slightly positive, but it's small. Then, as we go along the curve, the slopes are getting steeper and steeper, meaning more and more positive as we go. So this could be a graph of f double prime. Now let's make some connections here. In this region, f double prime is negative. So f double prime is negative when we are on the interval from negative infinity up to b. Now remember, when the second derivative is negative, then f should be concave down. Now let's go look at the graph of f. From negative infinity up until b, here's the shape of f, and it is concave down. So that makes sense. Back here to the graph of f double prime, we see from b on out, f double prime is positive, starting at b and going to infinity, which means f should be concave up whenever the second derivative is positive. And looking at the graph of f here, we see that it is concave up. You can also do the same with the graph of f prime. Wherever f prime is positive, the graph of f should be increasing. So f prime is positive from negative infinity to a, and we see on the graph of f, from negative infinity to a, f is increasing. So that makes sense. Then f prime is negative from a until c. All the values of f prime are negative on the interval from a to c, which means f is decreasing. Now, if we look at the graph of f from x equals a until x equals c, the graph is decreasing. So that also makes sense. And then we notice that the values of f prime are all positive from c until infinity, which means f is increasing. And when we look at the graph of f, starting from x equals c, going out to infinity, that's this part of the graph, is all increasing. So those are the relationships you have to see. From the graph of f, we can use the slopes to sketch a possible graph of f prime, and then we can use the slopes from the graph of f prime to sketch a possible graph of f double prime. In this example, make a sine line graph for f double prime of x to determine the intervals where f of x equals 4 over the quantity x squared plus 3 is concave up and concave down. So to get to the second derivative, we have to find the first derivative. Let's write f of x as 4 times the quantity x squared plus 3 to the negative 1. Now we can use the power rule and the chain rule to find the derivative. Then f prime of x would be negative 4 times x squared plus 3 to the negative 2, and then the chain rule tells us that we have to take it times the derivative of what's inside, which would be 2x. So let's write this as negative 8x times the quantity x squared plus 3 to the negative 2. Now, to get f double prime, we need to differentiate f prime. And to do that, we will need to use the product rule. So we've got f prime g plus f g prime that we need to do. Then f double prime of x is going to be the derivative of the first, which would be negative 8 times g x squared plus 3 to the negative 2. Bring down this plus sign. Then we have the first, which is negative 8x. So let's change this to subtracting 8x times g prime. And now to find g prime, we're going to have to use the chain rule. So that will be negative 2 times x squared plus 3 to the negative 3, because we have to subtract 1 from negative 2. Then the chain rule tells us we have to take it times the derivative of what's inside, which is 2x. Now let's clean up this derivative. We've got negative 8 times x squared plus 3 to the negative 2. Now over here we have a subtraction, but we have a negative coefficient inside, so that will turn it positive. 8 times 2 times 2 is going to be 32. We've got x times x, so that's x squared. And then we have x squared plus 3 to the negative third power. Now we need to factor. We can take out a coefficient of negative 8, and we can take out a factor of the quantity x squared plus 3 to the smaller exponent, which is negative 3. So we've got x squared plus 3 to the negative 3 out front. Now from this first term, what we would have left over is just an x squared plus 3. And from the second term, be very careful about the signs. Remember, we pulled out a negative 8, so we will have to multiply that times a minus 4 to get that positive 32, and the x squared. So now this is going to equal, this negative 8 will stay in the numerator. This x squared plus 3 to the negative 3 will have to go to the denominator. So that goes down here, x squared plus 3, and now that's to the positive third. Then we have this x squared minus 4x squared, which would be negative 3x squared plus 3. And that's in the numerator. Continuing to simplify, we've got negative 8 in the numerator. From here, we can factor out a negative 3, and then we would have x squared minus 1 left. Put that over x squared plus 3 cubed in the denominator. We can factor this difference of two squares, so now we have 24 times x plus 1, x minus 1 over the quantity x squared plus 3 to the third power. Now what we need to do is set this equal to 0 or undefined. in the numerator, we see that x equals -1 and +1 will make the numerator 0, while at the same time doesn't make the denominator 0. So those are roots. And for the rational expression to be undefined, we would need this denominator to equal 0, but it never does. Now what we do is make a sign graph using these x values. So we have x equals -1 and +1, and this is a signed graph for f double prime. Right at -1, we know f double prime is going to be 0. Same for +1. So now we can make a sign graph using test points. In this region, we could use a test point of -2. We know the 24 will always be positive. We know the denominator will always be positive. So for our test points, we only need to plug into these two factors. If we put a -2 here, we get a negative. If we put a -2 here, we get a negative. So that means f double prime will be positive. We pick a test point here, say 0. We would have a positive times a negative is a negative. And if we pick a test point of 2 over here, we have a positive times a positive is a positive. So the regions where f double prime is positive will be concave up. So that's here and here. And the regions where f double prime is negative, it will be concave down. So we can say f is concave up from -infinity to -1, union 1 to infinity, and f is concave down from -1 to 1. Find points of inflection on a graph. So what we do is find the second derivative, and then we find the x values where either the second derivative equals 0 or the second derivative does not exist. So that's going to feel a lot like finding critical numbers with the first derivative. It's just instead we will do it with the second derivative. Then we make a sign line graph for f double prime. And if f double prime changes sign at x equals c, then the point CF of c is a point of inflection on the graph. And we will abbreviate that with POI. Now, in the example above, we had already made our sign line graph. So let's take a look at that. We can see that f double prime changes sign right here from positive to negative. So that is going to be a point of inflection. It also changes sign over here from negative to positive. So that will be a point of inflection as well. So then that means to find the point, we need to get the y values for when x is -1 and x is +1. So let's find f of -1. Remember, we are plugging into the function, not the second derivative. So that means we have to evaluate 4 divided by -1 squared plus 3, which of course is 4 over 4, which is 1. So we have a point of inflection at -1, 1. We can evaluate f of +1, the other place on the sine line graph where the second derivative changed sign. So we will have 4 divided by +1 squared plus 3, which is 4/4, which is also 1. So that tells us we have a point of inflection at 1, 1 as well. So these are the places on this graph where there will be a point of inflection. And this point of inflection, because it's where the second derivative changes sign, then a point of inflection is going to be the place on the graph where the graph of f changes over from concave up to concave down, or it changes over from concave down to concave up. If we look back at our sine graph here, we see that from -∞ to -1, the graph is concave up. It will hit a point of inflection, and then it will change over to being concave down. Then it will hit another point of inflection and change over to being concave up again. Now, one thing to be careful about is that just because we have a 0 or a dne in the second derivative, that doesn't mean that it has to change sign. Those are just the places where it can change sign. In this example, we have to find any points of inflection on the graph of f of x equals x cubed minus 9x squared plus 27x minus 25. We know that in order to find points of inflection, we are going to need the second derivative. And in order to get the second derivative, of course, we have to first get the first derivative. So f prime of x is going to equal 3x squared minus 18x plus 27, and the derivative of a constant we know is 0. Now we can move on and find f double prime, which is going to equal 6x minus 18. We know that to find the points of inflection, we need to find the places where the second derivative is either 0 or does not exist. So let's factor this derivative, and we get 6 times the quantity x minus 3. We set that equal to 0 or does not exist. Since the second derivative is linear, we know it exists everywhere, so it's never going to have an x value where it doesn't exist. And it will equal 0 whenever the quantity x minus 3 is 0, and that happens at x equals 3. So now we will make our sine graph. We put on x equals 3, and we know the second derivative is equal to 0 there, and we need to plug in test points. If we were to pick a test point of 2 in this region, we can see it's going to make the second derivative negative, which means the graph is concave down. If we were to pick a test point of 4 over here, that makes the second derivative positive, which means it's concave up. Because the second derivative changes sign at x equals 3, that means there will be a point of inflection there. So we need to figure out what f of 3 is in order to get the y value. So that's going to be 3 cubed minus 9 times 3 squared plus 27 times 3 minus 25. And this is going to equal, well, it's kind of easy to see right here. We have 3 times 3 times 3 times 3, and we have the same thing here, 3 times 3 times 3 times 3. So both of these are 81. They're going to cancel out, and we just have to do 27 minus 25, which is 2. So there will be a point of inflection at 3, 2 on this graph. In this example, we have to sketch the graph of f of x is equal to x to the fourth minus 4x cubed. We know the first thing we need to look at are the roots, and that's the places where the function is equal to 0. So x to the fourth minus 4x cubed has to equal 0. We can factor out an x cubed, and we have left x minus 4 equals 0. And we can see we will have a root at x equals 0. And of course the y value is 0. That's what it means to be a root. We will also have a root at x equals 4. The y value is 0 there. So let's go ahead and put those on our graph. There's a root at 0, 0, and a root at 4, 0. Now the domain of this function, of course, is all real numbers, so we know that this graph goes from negative infinity to positive infinity. So it's a good idea to make a note of that. Our domain is all real numbers. You can either write it as negative infinity to positive infinity, or you can say x is an element of the real numbers with the double-stemmed r. Next up, we need to find the relative extrema. And of course, extrema means minimums and maximums. So we will do that with the first derivative test. F prime of x is going to equal 4x cubed minus 12x squared. Let's factor that. So that will equal 4x squared times the quantity x minus 3. And to find the critical numbers, we will set that equal to 0 or does not exist. Because f prime is a polynomial, we know it exists everywhere, so there's never an x value where it does not exist. To find where the derivative is 0, we see that will happen at x equals 0 and x equals 3. These are the critical numbers. And we know that it's the critical numbers that we have to put on our sign graph for f prime. So let's line these up. X equals 0 is the y-axis, so we can put that there. And we know that the derivative is 0 there, which means the graph will have a horizontal tangent line at that location. The other critical number is x equals 3, so we line that up with the 3 on the graph, and we will have a horizontal tangent there, because of the 0 in the derivative. Now we have to fill in with the signs. If we pick a test point over here, we could choose -1. Now this piece of the derivative is always positive because of that squared, so I'm not going to bother plugging anything in there. The only quantity that will determine the sign of our derivative is x minus 3. So remember, we had a test point of -1. If we put -1 in for x, this is negative, which means f is decreasing. A test point in here, we could choose 1 or 2. Either way, this is negative, which means the graph is decreasing. So notice, even though we had a critical number here, the derivative did not change sign. Remember that the critical number is the places where the derivative could change sign. Now, let's pick a test point over here, which would be x equals 4, and we will get a positive. Now that makes the graph increasing, and we can see because the derivative changes over from negative to positive, that means we will have a min there, a relative min, and it's okay to just write min. Now to find out the y value of the min, we need to plug x equals 3 into the function. So we need f of 3. And of course we're plugging into f of x here. So we have to go 3 to the 4th power minus 4 times 3 cubed. Now if you are doing this without a calculator, one thing I would recommend is let's factor out 3 to the 3rd. And then what we would have left is 1/3 from here minus the 4 from here. Now it's a pretty easy calculation to do in your head because you have 27 times -1, which is -27. So this graph is going to have a relative minimum at 3, -27. Now to plot that point, obviously we don't have 27 marks on our y-axis, so we pick some interval to go by. Maybe we'll go by 4s. So we have -4, -8, -12, -16, -20, -24, and -28. Then that means this minimum of 3, -27 is going to be about right here. We know there is a horizontal tangent there, and we know that a minimum will have to look like this, a smooth curve. Next up, we will look at the concavity, which means the places where the graph is going to be concave up or concave down, and determine if there are going to be any points of inflection. And for that, we need the second derivative. So f double prime of x, I would suggest using this first form of the derivative, the unfactored form of the derivative, because it's easier to find the second derivative. So from the first term, we are going to get 12x squared, and then the minus sign. And from the second term, we are going to get 24x. Let's factor that. We can pull out a 12x, and we would have left x minus 2. and we know that we will set that equal to 0 or does not exist. Because the second derivative is a polynomial, it exists everywhere. So we know that there are no x values where it does not exist. It will equal 0 whenever x is equal to 0 or x is equal to 2. And we will need to take those values and put them on our sine line graph for f double prime. So x equals 0 needs to line up with the 0 on the graph. We know that the second derivative equals 0 there. This would be x equals 1. This is x equals 2. So let's bring that down. We know the second derivative is 0 there as well. Now we have to do our analysis. In this region, we can pick a test point of -1. If we put -1 here, this is negative. If we put -1 here, this is also negative. A negative times a negative is positive, which means the graph is concave up there. A test point here would be x equals 1, so we would have a positive times a negative, which is negative, so the graph is concave down. A test point in this region would be x equals 3. Putting a 3 here is positive. Putting a 3 here is also positive. So the graph will be concave up there. Now let's analyze our sine line graph for f double prime. Because the second derivative changes sign at x equals 0, that means there will be a point of inflection there. So let's find the y value by plugging in f of 0. Well, we actually already know that. Remember that it was one of our roots, and we know that that's equal to 0. So we will have a point of inflection at 0, 0. We see at x equals 2, the second derivative also changes sign, so that will be another point of inflection. F of 2 is going to equal 2 to the 4th minus 4 times 2 cubed. And once again, you can factor out a 2 to the 3rd if you like, or these numbers are small enough where we could just multiply them out. 2 to the 4th is 16. 2 to the 3rd is 8. 8 times 4 is 32. So we're subtracting 32, and this is -16. So we know we have a point of inflection at 2, -16. So we can now put these points of inflection on our graph at 0, 0, and 2, -16. So we have 0, 0, we know now is a point of inflection, and 2, -16 is also going to be a point of inflection. Now, one of the things that I suggest you do to start drawing your graph and figure out how these points are going to all connect is to make what I call the combo graph. So what I suggest you do on the combo graph here is put any x value that appears on either the sine graph for f prime or f double prime. So that means we will put x equals 0, which we know is a point of inflection. we will put x equals 2, which we know is also a point of inflection, and we will put x equals 3, which is a minimum. Now, from negative infinity up until 0, we see that the graph is going to be decreasing and concave up. Now that has to look like this. So now we can go to our graph and draw from negative infinity to 0 a curve that looks like this. So here, from negative infinity until 0, the graph is going to have to look like this, decreasing and concave up. Now let's see what's happening between this point of inflection and the next point of inflection. Between 0 and 2, the graph is going to be decreasing and concave down. So we know that that has to look like this. So connecting the first point of inflection to the second point of inflection means we have to draw a curve that is decreasing and concave down. So let's go up to the graph and do that. Decreasing and concave down. Now, from x equals 2 until x equals 3, we see that the graph will be decreasing and concave up. Well, that has to look like this. So we go up to the graph and we can connect that point of inflection to the minimum, and it's going to be decreasing and concave up, and that makes perfect sense with what we knew the curve of the minimum had to look like. And then the rest of the graph from x equals 3 to infinity is going to be increasing and concave up. So that's going to have to look like this. And the great thing about drawing these curves from the combo graph is you get an overall view of what the graph has to look like, and then you add those components in. So now from 3 to infinity, we have to draw a curve that's increasing and concave up, and draw this curve increasing and concave up. And this is our final graph. Next up, we will learn about the second derivative test, which finds relative extrema, not points of inflection. So even though it's called the second derivative test and uses the second derivative, it's not finding points of inflection. So it's not like the sine line graph for f double prime. This test actually uses both derivatives to find relative extrema. Now for this test, the first requirement is that the derivative at a certain x value, c, has to equal 0. Now we know that means there's going to be a horizontal tangent on the graph. If the second derivative is positive, that means the graph has to be concave up. Well, if a graph has a horizontal tangent and is concave up, the only thing that could be happening at x equals c is a relative minimum. If instead the first derivative is 0, meaning we have a horizontal tangent, and the second derivative is negative, meaning that it's concave down, then that means the only thing that could be happening at x equals c is a relative maximum. So next we'll try an example and see how this rule works. In this example, we have to use the second derivative test to find the relative extrema. Now remember, in the second derivative test, we will have to find f prime and then set it equal to 0. Notice that it's not going to be set equal to a dne. We don't want to find the places where the derivative does not exist. We only want to find the places where the derivative is equal to 0. So f prime of x is going to equal negative 15 x to the fourth plus 15 x squared. We can factor out a negative 15 x squared, and then what we will have left is x squared minus 1. Now, of course, that factors into negative 15 x squared, x plus 1, x minus 1. And now we are going to set that equal to 0. And that's going to occur when x is equal to 0 from this first factor, when it's negative 1 from the second factor, and when it's positive 1 from this third factor. So what we will do now is put those values into a chart. So our x values are negative 1, 0, and 1, and we know the value of the derivative at each of those x values is 0. So we have 3 values for c in this case when we talk about f prime of c has to equal 0. We know the derivative is 0 at all 3 of those x values. Now, the second part of the second derivative test hypothesis is that we need to determine whether the second derivative is positive or negative at those locations. So we will decide that from looking at the second derivative. Now let's use this unfactored form of the first derivative to find the second derivative. F double prime of x is equal to negative 60 x to the third plus 30 x. And now all we need to know here is whether each of these values will yield a positive or a negative for f double prime. So f double prime of negative 1 would be, from this first term, we would have a negative 60 times a negative 1, so that's a positive 60. Here we have 30 times negative 1, that's minus 30. This is equal to 30, which is a positive number. So because the first derivative is 0 and the second derivative is positive, we know that could only happen at a relative minimum. We know the x value is negative 1, and we will have to plug into f of x to find the y value. We know that f of negative 1 is going to be negative 3 times negative 1 to the fifth plus 5 times negative 1 to the third, which is equal to a positive 3 minus 5, so that's negative 2. So we know there's a relative minimum there. If we look at f double prime of 0, which is the next value we need to check, we see that we would get 0 plus 0, which of course is 0, and 0 is neither positive nor negative. So that means no conclusion possible here from the second derivative test. And then finally, we will plug in x equals 1 to the second derivative. If we plug x equals 1 into this first term, we are going to get negative 60 plus, if we plug x equals 1 into the second term, we get 30. Negative 60 plus 30 is equal to negative 30, which is a negative number. So if the first derivative is 0, meaning we have a horizontal tangent, the second derivative is negative, meaning we're concave down, that must mean that we have a relative max, and that's going to be at 1. And then to find the y value, we will need to plug into f. So f of 1 is going to equal negative 3 times 1 to the 5th plus 5 times 1 cubed, which is going to equal positive 2. So using the second derivative test just means you're looking at the sign of the second derivative at the locations where the first derivative is 0. If you have a horizontal tangent and you are concave up, that has to mean you have a relative minimum. If you have a horizontal tangent and you are concave down, that means it can only happen at a relative maximum. In this example, we will also use the second derivative test to find the relative extrema. We are given that g of x is equal to 4 over x squared plus 3, and earlier in the notes on page 2, we found g prime and g double prime, so we will just write those in here. We don't need to compute them again. Now we know in the second derivative test, the first part of the hypothesis is to take the derivative and set it to 0. Remember, we never look for the places it does not exist. We only look for the places where it's 0 in the second derivative test. Now, a rational expression will equal 0 when its numerator is 0 and its denominator is not 0. Well, in this case, our denominator will never be 0 because we have x squared, which is greater than or equal to 0, plus 3. So this denominator is always positive. We don't have to worry about it equaling 0 ever. Then the only place g prime will be 0 is when x is equal to 0. So that's the x value where we will do our analysis. We know the derivative is 0, and now we need to determine if g double prime of 0 is positive or negative, and then we can make our conclusion. So here we would have 24 times 1 times negative 1 over a positive number, because this denominator will also be positive. So looking at this, we can see it's going to be a negative number. If the second derivative is negative, where the first derivative is positive, then our conclusion is that a horizontal tangent and concave down will lead us to a relative max. The x-coordinate is 0. We have to plug 0 into the function, so g of 0 is going to equal 4 over 0 squared plus 3, which is 4/3. So because we had a horizontal tangent and we were concave down, that tells us we will have a relative max at 0, 4/3.